Right, good morning. Right, we are now moving on to alternating currents, the one we are saying AC. So after this lesson, here are the key points that you must know. These are the objective. The first point, you need to understand and use the terms period, frequency, peak value, root mean square value as they are applied to alternating current or voltage. You need to deduce the mean power in a resistive load as half of the power of sinusoidal alternating current. Like represent the sinusoidally alternating current or voltage by this equation. You also distinguish between the root mean square and the peak values, and also recall that the root mean square value is the peak value over square root of 2. You need to understand the principle of operation of the simple laminated iron core transformer and recall that for an ideal transformer, a number of turns in the secondary coil is divided by number of turns in the primary coil is equal to the voltage in the secondary coil over voltage in the primary coil is also equal to current in the primary coil over current in the secondary coil. You also need to understand the sources of energy loss in a practical transformer. You also need to appreciate the economic advantages of alternating current and high voltage for transmission of electrical energy. You also need to distinguish between half-wave and full-wave rectification. You also need to explain the use of a single diode for half-wave rectification of an alternating current, and also the use of 4 diodes bridge rectifier for full-wave rectification. And also the importance of capacitors in smoothing. You also need to know that include the effect value of the capacitance in relation to the load of the resistance. So what is an alternating current? You need to know the difference between alternating current and direct current. Here are the two graphs which really distinguish the difference between an alternating current and a direct current. As you can see from those two diagrams, an alternating current changes direction continuously. That is, it vibrates backwards or forwards. So this one is the graph for the alternating current. This one is the graph for the alternating current. It's like a sine graph. That's why we say it's a sinusoidal graph. And this one is the graph for the direct current. It's only in one direction, in the positive direction. Here it changes, alternating current changes from backwards to forwards. So you need to take note of these formulas. It is the terminology used, and you can also relate to oscillations, the one that we have done in oscillations. So we are saying this one is our graph, and the one we are referring to I naught is the maximum or peak value of current. Then the frequency of the alternating current is 1 over t. So meaning to say the frequency is of the signal is the number of complete oscillations per unit time, and t is the period, the time taken for one complete oscillation, and peak value, the one we have indicated, the maximum value of current or voltage. So the equation, these are the two equations which represent. It says sinusoidal graph is written in this form: x is equals to x naught sine omega t. X can be represented by current or voltage. So this one is our equations. Current is equals to current peak value cos 2 pi f. That is, if the graph starts at the maximum, it will be in the cos, but These are the general equations for the current, the sine graph. But if it is a cosine graph, you will be using this one. But if it is a sine graph, you will be going to use this one. Remember from oscillation that omega is 2 pi f, or omega is 2 pi f. So this can be reduced to current is equals to maximum current, then sine omega t. Similar for voltage, still the same thing for voltage. Right, let's look at this example. Let me try to zoom this one. Determine from the diagram the period, the frequency, the peak value, and the peak to peak voltage. Right, as you can see, the period, that is the time taken for one complete oscillation, that is from here, this will be our complete oscillation to here. So as you can see, it's 0.02 seconds, time taken to complete one oscillation. Then the frequency from this formula is 1 over t, so it will be 1 over 0.02, which is 50 Hz. Then the peak voltage, that is the maximum voltage, as you can see, the maximum voltage is 340, because there are 1, 2, 3, 4, 5. Each small box represents 20. So the peak is 1, 2, that is 340 volts. That is our peak voltage. Then the peak to peak range, that is from minus 340 to 340. So the range peak to peak voltage, that is 340 plus 340, we're going to get 68 voltage. So as you can see from our diagrams here, before we move on to the transformers, if you want to look at power dissipated by an AC current in a resistor, it's given. Remember that power is equals to I squared R. Power is given by I squared R. But since we have said current, remember we said current is also equal to I naught sine omega t. So where there is I, if we substitute with this one, we are going to get this one. Then if you square I naught squared sine squared, right? So this one is the graph for current. This one is the graph for current. And for the power now, we are going to square this current graph, meaning to say this peak value is going to be squared. So it will be like this. Maybe if suppose this value was supposed to be 3, if the peak value is 3, then h the power, it will be like 3 squared, then you have 9. And as you can see, the graph of power, we don't have negative values, meaning to say if you square this part, it is going to be in this part. So this is the part. So this is the graph for power. It is always in the positive. And this is our peak. As you can see, this is our peak power, P naught. Here we have our P naught. Then half of P naught is what we are saying is the mean power. Half of P naught is what we are also saying It's the mean power. Yeah, you shall see when we are going to work that. So if you study the curve above, the power curve is always positive. Even though current goes negative, power is equal to current squared, and the square of the negative number is always positive. So like what I have highlighted, this one is the power average. That is, it is going to be a peak current squared times resistance. So the direct current that will be dissipated by this power, it will be direct current I naught over root 2, and we are saying this direct current is known as the root mean square of current. The root mean square of current. So you need also to define that. This is the definition. The root mean square value of current or voltage is the value of direct current, please. This is the value of direct current or voltage that would convert energy at the same rate in the resistor. So that is the root mean square value. It is the value of current or voltage that would convert the same energy or power at the same rate in the resistor. So that is the root mean square value. Here we have this worked example. Here. So to explain what is meant by the statement that the mains voltage is rated at 230 volts, 50 Hz, calculate the peak value. So if the mains voltage is rated at this one tells us the root mean square voltage is 230. So that is our root mean square voltage. So from this formula, if you want to find the peak V0, you're going to say the root mean square voltage times root 2. And we are going to get 325 ohms. Then for part B, calculate the energy dissipated when the electric fire of resistance 25 ohms is run from the supply for 1 hour. So remember power first. Remember power is equals to power is equals to energy over time. So for energy, if you multiply power times time, that's why we are seeing this time here, this time. Then we're going to say the root mean square voltage squared over resistance. Remember power is equals to V squared over R. So if it is energy, we multiply this by time. So the time is 1 hour. That's why we are saying 2 seconds 60 times east. And the energy is going to be 7.6 times 10 to the power of 6. So that is all about the root mean square values, how we calculate them. So here is also another formula for the root mean square. The root mean square value of an alternating current is the value of the direct current that will give the same heating effect when the connected in the same resistor is the same, the one that we're talking about. Now let's move on to transformers. What are transformers? Transformers, these are electrical devices that are used to increase that we are saying to step up, or to decrease, to step down AC voltages. So if a voltage is increased, the alternating current will decrease, and vice versa. You must know that if a voltage is increased, the alternating current will decrease. and vice versa. So step down, step up transformers increase step up voltages and decrease currents. Step down transformers decrease step down voltages and increase currents. So here is a structure. This one is the symbol for a transformer. You must know this symbol. And here is the transformer. It shows the main component of a transformer. Here is the primary coil. Here is the secondary coil. As you can see, this transformer is a step down. A step down, they've got the number of turns, main number of turns in the primary, then a few number of turns in the secondary. Whereas a step up is got few numbers of turns in the primary, then main numbers of turns in the secondary. So here are the main components of the transformer. We have the primary coil and the secondary coil, and we have voltage supplied to the primary coil. Here we also have voltage for the secondary coil. So this NS represents the number of turns of the coil. Then this one now is the laminated iron coil. So we are going to look at how it functions. So here is how it functions. An alternating voltage from the primary coil causes an alternating current to pass through the primary coil, which induces changing magnetic flux inside the coil and the iron ore. So if current passes this one, it is going to induce a changing magnetic flux inside the coil and the iron ore. So this changing flux passes around the iron ore and links with the secondary. So the changing flux passes around this iron ore and links with the secondary coil. So the changing flux linkage, it is changing because of the AC current which is being supplied. It is always changing. So the changing inside the secondary coil induces the alternating voltage in the secondary coil. Hence, from Faraday's, it can be shown that voltage in the secondary coil over voltage in the primary coil is also equal to number of turns in the secondary divided by number of turns in the primary. Right, this will be an ideal transformer. It's only for ideal transformers where we are saying there is no energy loss. The transformer is 100% efficient. So you need to remember this one for the ideal transformer. Also, you need to take note. The core of a transformer is usually made of soft iron with low carbon content, making it easy to magnetize and demagnetize, reducing hyperthrust losses. Right. Then for your real transformers, the one we are saying practical transformers, they are not always 100% efficient, but there are some energy which are lost. And the table below shows the main energy losses. Loss, then copper losses. We have copper losses, we have iron losses, we have magnetic hysteresis. So copper losses, it causes the coils of wire. The wires, they are made up of copper. These wires, they are made up of copper. So we are saying in the copper losses, the coils of the wire have resistance. Energy is lost through heating of the coils. So the method of reducing, we use low resistance wired links, e.g. large diameter of copper wire. Then in iron losses, this iron, we also have losses in this iron. And let's say we have what we are saying eddy currents, loops of currents induced in the iron ore by changing magnetic field cause heating of the coil. So energy is being also lost on the ion through which it passes the induced EMF to the secondary coil. So the method of reducing it, we have to laminate the iron ore. So the core is made up of thin sheets of iron separated by layers of insulating material. The core then has high resistance in the direction of the eddy current. So if you laminate the iron, you're going to prevent the eddy current. Then we also have what we call the magnetic hysteresis. It's energy lost through repeated magnetization and demagnetization of the iron ore. So one way of reducing it, the core is made up of soft iron with a low carbon content, which easily magnetized and demagnetized without much energy loss in the transformer. So for any ideal transformer, we can use this formula, the one that you are seeing. This one for an ideal. Let's look at an example where it's saying an electric train is designed to operate at 12 voltage AC. Calculate the turns ratio for a transformer to be suitable to step down a mains of voltage. This one. So here we have the voltage in the secondary, then divided by the voltage in the primary. It's the same as number of turns in the secondary over number of turns in the primary. And here this one, since it is a step down, this one will be our primary and this one will be our secondary. So it's 12 volts over 230. So the ratio will be 1:19. So that is the one required. Then in any ideal transformer, the power output will be equal to the power input. So VSIS is equal to VP IP. We also have this with example where we are saying a 12V 96 watts heater is run from a transformer connected to the mains of 230 supply. Assume that there is no energy loss in that transformer, which is meaning to say it's an ideal transformer. Calculate the current in the heater and the current input into the transformer. So from the formula, power equals to VSIS, you can find that the current will be power over voltage. Then the power it's 96 watts divided by its voltage. That is the current in the secondary coil, which is equals to 8 amps. Both it's a domestic appliance, so we have applied the step down. So meaning to say this one is our VS and this one is our VP, the primary in the primary. So we want to find the current in the input of the transformer, that is the primary current. So also going to use this formula. VSIS is equals to VPIP. So VS it's 12, the voltage in the secondary times its current, the one we've calculated, is equals to voltage in the primary times current in the primary, and we are going to see that our primary is 0.42 amps. Like what we've said for real transformers, in practice, transformers, although they can be designed to have efficiencies in excess of 99, but they can never be 100% effective. Energy is always lost. We've already looked at it. Work done in overcoming resistance in copper coils. It's usually made up of copper, hence energy losses. And these are known as copper losses. We've highlighted that the induced currents in iron, known as eddy currents, energy always lost. Work done in the transformer of magnetic fields, in the iron ore. These energy are known as hysteresis losses. The energy losses due to the resistance is always kept minimum by making the coil out of a good conductor such as copper. In step-up transformer, the input current is large, so the fewer turns required are made of thick wires. The secondary coil, which carries the small current, is made up of thinner wires. You also need to take note of this. So the iron losses are reduced by laminating the coil. This means that making it out of the thick iron plates, each plate is being insulated from the neighbors by thin layer of varnish. This reduces the size of eddy currents induced. Then the hysteresis losses are reduced by making the coil from pure iron, which is easily magnetized and demagnetized, rather than from steel, which requires much more work to magnetize and demagnetize. Before we move on to rectification, we need to talk about transmission of electrical energy. We also need to know the advantages and disadvantages, the advantages of alternating current and high voltage. Electrical energy is transferred from power station across many kilometers of power lines to local communities. Although cables are thick and made up of metals of low resistance, still energy is dissipated. Remember, energy dissipated in the cables is I squared R, where R is the resistance of the cable. So the smaller current, the less the energy is wasted. Indeed, if the current is halved, then the power loss is reduced by the factor of 4. Consequently, energy transmitted at higher voltage, low current. So, mean to say high voltage transforms low current and then step down before being distributed to the consumer. Alternating current are used for transmitting electrical because an alternating voltage can be stepped up or stepped down with much less energy than direct voltage. So this is the most basic advantage why we use AC. We use AC because we can step it up or step it down using a transformer. Here's an example. It's a model transmission line that we are given here. So in this diagram here, they are saying what shows a demonstration that a teacher does to show energy loss in a transmission line. The two resistance wires have a total resistance of 2. The lamp is designed to run at 12 volts and to transfer energy at a rate of 36 watts. But you need to calculate the resistance of the lamp and the total resistance of the circuit. Assume that the resistance of the lamp does not change with the temperature. B, want to calculate the current in the circuit. C, we also need to calculate the drop in potential difference across the resistance of wires. We also need to calculate the power loss in the resistance of power dissipated. As you can see here, we want to find the resistance of the lamp. Resistance is given by, if you use the formula power is equals to V squared over R. And if we make our R the subject, we are going to see that the resistance of the lamp will be R is equals to the voltage squared divided by power. So as you can see, our voltage is 12 and our power is 36. So we are going to have the resistance of what? Of 4. So the total resistance in the circuit, it's the ones that we have the total resistance of the wires plus 4, which is 6. Then part B, the current in the circuit, we are going to say the voltage over the total resistance, which is 2. We also need to calculate the drop in potential. Potential drop of the wires is equal to resistance of the wires times the current through them. So the resistance of the wires, which is 2, times current through them is 4. So power dissipated in the wires is equal to potential across the wires times current. So the potential across the wire is 4 times the current. So power dissipated is 9. It's 8 watts. So power dissipated in the lamp is equal to potential drop, that is 12 minus 4 times 2, which is 16 watts. Right. Here is an exam tip. You can pause it, also read this exam tip. It's very important. Now we want to look at what we call rectification. So rectification is a way of obtaining direct current from AC. So we have what we call the half-wave rectification. Although it is adventurous to transmit power using alternating current, many electrical appliances requires direct current. The simplest way to convert alternating current supply to direct current is to use a diode. So a diode helps us to convert alternating current to direct current. So for the first one, we have a half-wave rectification. Here, this is the supply, and we have this diode, which always allows current to pass through in one direction. So if we are to take this V out here, firstly we have our AC from positive to negative, backwards and downwards. But if you put a diode, we are going to have this half-wave rectification. We only have the positive path. So the negative, it's like current can't move in this direction. So this V out, you are only taking current in the positive only. The only current moving in this direction. Maybe we can refer it to the positive. That's why our graph is showing the positive. So the half wave is not always ideal for appliances like televisions, because you can't watch a TV for this time, then it shuts down. Then for this period of time, then it switches on, then shuts down, then switches on. So there are some appliances that are not ideal for half-wave rectification. Maybe if you can say maybe some irons, yes, we can say we can use half-wave. So we can move on to full-wave rectification, whereby we want a full flow of direct current. We are going to use this diagram. It shows how we can obtain a full wave rectification. As you can see, if current is moving upwards here, this and this will conduct. Because current will go through B, then after this, then it will go through this V out, then this one in this direction, then from the original. And also if it is current is coming from this one, so C and A will conduct. So as you can see, current always passes through this point in one direction, no matter what. So this is the explanation here. As you can see, when P is positive with respect to Q, that is current moving from here to here, then the current will pass through P, through diode B, and through the resistor through diode D, like what I'm saying. Right, I think that one's okay. Then our full wave rectification will be in this. It will be in this form. But again, we have a problem. We might have appliances that might not need the voltage to reach to almost zero. As you can see, our graph indicates that voltage increases to a maximum, then also decreases until it also reaches zero. Then it takes a short time to peak. Yes, but it's not ideal for other appliances. So what can we do now? We need to put a capacitor in parallel with the resistor, like in this way. If you put a capacitor in parallel with the resistor, maybe in a full diagram like this, maybe our diagram will be in this. If they say, can you draw a full diagram where we have a capacitor in conduct light, like this one? Here I think will be the diagram like this. So meaning to say our capacitor is going to make some smoothing, like saying in this case, if we put a capacitor in parallel, it is going to discharge when the voltage starts to fall down. It is going to discharge at the moment when the voltage starts to decrease. Then the capacitor will discharge. Then the voltage will increase up to the peak. Then at the moment when it is now about to fall down, the capacitor will discharge, and you obtain this graph in this form. This one is the smoothed. I'm saying smoothing circuit, and then the smoothed output produced by a single capacitor. So it's how a capacitor works. So because the capacitor takes time to discharge, it will only partially discharge in the time it takes the potential difference to rise once or more. So the value of the product, capacitor times resistance, is much greater than the time period of the original alternating input. This means that the capacitor does not have sufficient time to discharge significantly. So you also need to know that the product of capacitance and resistance is what we are referring as to the time constant. Is the time taken for a charge to fall to 1 over E of the original charge. So that's all. Maybe if we can find a way. So it's still the same thing that we're talking about here. So this is all about AC currents. We need to define the direct current, alternating current, also transformers, and also we also need to know the full wave and half wave rectification. So this is all about AC currents. I hope we have understood, and I hope we have managed to answer all these key points. Have a good day.